Hello everyone. I'm Nishtha Sharma and I'm 13 years old. And today I'm super excited to show you BatRobot, a RAS2 manipulator that I built. It works with Alexa, it has custom object detection, and uses motion planning to move in the real world. But before I tell you more about the robot, I want to briefly talk about my journey because every part of this robot comes directly from what I learned step by step. So, So I started my journey with Python, where I learned how to think logically, how to break complex problems into simpler tasks, and how to write programs that actually do useful work. So from there, I learned Flask, SQL, and automation, and I got a deep understanding of how the backend systems work. And after that, I also learned how to collect data, process it, and build something meaningful using it. And after that, I learned web development using Node.js, Express, and REST APIs. And I got a deep understanding of system integration and how different components communicate, which was extremely important for robotics. But after some point of time, I didn't just want software on screen. I wanted to see real movement, real servos, real sensors, and that's when I moved into ROS. I learned ROS from the construct where I got hands-on experience on building nodes, topics, services, actions, launch files, etc. And suddenly I realized that everything that I had learned before started making sense in the context of robots. So now I wasn't just printing logs, I was moving servos. So after that, I realized that if I want to build my own manipulator, I have to learn mechanical design, and that's when I picked up Fusion 360 and started designing parts. So printing them, breaking them, redesigning them, and then printing them again. And I also learned 3D printing using Cura, including calibration, orientation, and minimizing support structures. And I also learned how to code Arduino in C++, connect and control servos, and integrate electronics with ROS. And after a lot of trial and error, BatRobot was finally born. And I put everything into it: software, ROS, electronics, system integration, all of it. And here's a fun fact that I've probably said Qualcomm build more times than my own name this year. And you can click on this link to see the robot move in action. Can you please play it? So here you can see this is my robot. I'm sorry it doesn't have a gripper. I tried to print it but it couldn't. And here I type the command. So this is a launch file that launches the real hardware. So I use Arduino as the hardware interface. And here you can see the robot. It's a bit slow but it works. So here is the MoveIt, and here I am giving some positions, target positions. So I'm moving it. Okay, so now I'll hit plan and execute in the MoveIt, and you can see that the robot starts moving. Okay, so now that you've seen my journey, Okay, so now you have seen my journey. So now let me talk about BatRobot. So BatRobot is a fold-off 3D printed manipulator built using ROS2 Humble. It uses Arduino as the hardware interface, and the entire ROS site is organized into 6 functional packages. And Bat Robot has three core capabilities, which includes voice control, computer vision, and motion planning. For voice control, Bat Robot listens to Alexa. When I say activate robot, Alexa triggers a skill that sends the command through the NG-ROC tunnel into my local RAS2 system, where the robot receives it as a task request and executes the action. For computer vision, I've trained a custom model to recognize pen from a USB camera with real-time coordinate extraction. And for movement, Bat Robot uses motion planning, inverse kinematics, and trajectory generation through ROS2 and the custom controllers so that the robot can move to the target position safely and avoid the unsafe configurations. So you can click on this link to see my robot move in the simulation. And can you please show the robot move in the simulation? So here I go into my directory, and so here I'll type the command that will load the simulation. So gazebo move it. So here I launch the simulation.launch.py, and you can get the full code on my GitHub. So here it launches MoveIt and Gazebo. So here I will do the same thing. I will give it some commands, some target positions, and the same thing will happen in Gazebo. So however I move in MoveIt, the same thing will happen in Gazebo. So now I'll hit plan and execute, and you can see the robot moving in Gazebo. Okay. Okay, so let's move on. Now looking at the core architecture, I use Arduino as a bridge between ROS2 and the real hardware. ROS2 sends join commands over serial, and Arduino converts them into precise PWM signals that drive the 5 servos. And Bat Robot is divided into 6 functional packages, which includes description, controller detection, planning, firmware, and voice interface. Each package has a single responsibility, which makes the system easier to debug and scale. And every structural part, like the base, link, shoulder, joint, all of them are designed in Fusion 360 and 3D printed, which makes the robot lightweight, affordable, and fully customizable. And yes, it's called Bat Robot because it literally hangs out in my workspace and swoops into action when I call it. So now that we've seen what Bat Robot looks like, let's quickly go inside the system and see how everything flows through ROS2. Bat Robot follows a layered architecture, and this slide shows how information enters and moves through the robot. So the first layer is the task reception layer. When I give a command through Alexa, the voice command is converted into a task number and sent as an HTTP request through NGROC into my local RAS2 system, where the Alexa interface node receives this and publishes this on the task command topic. So now the robot knows what to do. Next is the perception layer. So a USB camera publishes images on camera image raw topic, and a YOLO node subscribes to the stream, runs real-time inferences, and publishes the detected objects. So next is the planning layer using MoveIt, which solves inverse kinematics, checks for collision, and generates safe trajectories for the arm. Since MoveIt does not directly control the servos, execution happens through the control layer using ROS2 control. And next is the hardware layer. So I use Arduino as a bridge between ROS2 and the real hardware. So it receives joint commands over serial and publishes them as on RAS2, and then Arduino converts them into precise PWM signals that drive the fire servos. So this is the launch file. You can get the full code on my GitHub again. And this loads the full mode of the robot. So it launches the voice control and the motion planning. So at the top, I define a function that loads the robot description. This is where the BAT robot UIDF model and the controller configurations are loaded. So instead of hard coding everything, I load them into reusable MoveIt configuration objects, and uh, so I load them into reusable MoveIt configuration objects, and then I start the task server node. This is the brain that listens for commands on the task command topic, and then I load the Alexa interface node, which listens for incoming requests on the topics and then publishes them as a standard ROS2 message. So, programmatically, the vision pipeline starts with the camera node, which captures frame using OpenCV, and then a YOLO node launches and subscribes to the stream, runs inferences on each frame, and publishes the filter detections with the bounding boxes. And these are sent as a standard ROS2 message. And then a separate post conversion node takes the bounding box center, applies calibration, and converts it into a 3D target pose relative to the robot. So this is the launch file used to launch the YOLO detection. So the entire vision pipeline launches. So first the camera node starts, which initializes the driver setting, and immediately after that the YOLO node launches and subscribes to the stream, runs inferences on each frame, and publishes the detections as a standard topic message. And then a post conversion node takes this and converts it into a 3D target pose relative to the robot, and launching everything through one file ensures that all the nodes start in the correct order and everything stays time aligned. And you can click on this link to see the YOLO object detection work. Can you please do that? So here I have written the command that loads the code for the detection, and here you can see I have trained a custom model to recognize pens. So for voice control again, um, so this is the voice control, and you can see that when I give a command through Alexa, for example turn right or turn left, it is converted into a task number and that is sent as an request, so as a task ID through ngrok, which exposes a secure temporary URL to my local ROS2 system, where the robot receives it as a task request and executes the action. And sometimes I also forgot to say, hey Siri, move the robot instead of Alexa. And you can click on this link to see the voice control work. So here I start the ngrok tunnel on port 5000. Then I copy the URL which it provides. And this is the Alexa developer console. So I've trained the model. So I've given some positions already. So like turn left, turn right, and activate robot. So it does all of that. So I've pasted the endpoint, and now I will test the robot. So here I can type commands, and first I will load the gazebo, Arvis and the Alexa interface node. So now I've said activate robot, and then you can see that the robot moves in gazebo. So yeah, you can close this now. Okay, so this is the Arduino firmware that loads all the 5 servos of BatRobot, and it is the final safety and timing layer of BatRobot. So it receives joint angles over serial from ROS2 and parses them into 5 target angles, and then immediately checks each value against the safe joint limits. And then at startup, the code initializes the serial communication, attaches each servo to its PWM pin, and moves the robot into a safe starting pose. And in the main code, the Arduino waits for the complete command frame, and if no new commands arrive within the timeout window, it either waits or it returns the robot to safety. And now let's move. So this project did not work on my first try, or the second, or the 20th. The first big failure was with MoveIt. Motion planning kept failing because the start states were slightly unreachable. The solution: I carefully validated the joint limits and tested the poses in Arvis. Next is the YOLO detection. So it was detecting objects but nothing moved, and the solution was that I carefully traced messages across topics and tuned motion for real world physics. Next was the sim to real gap. So whatever seemed to be working in the simulation caused jitter and stalling on the real robot. And I fixed this by adjusting torque, added firmware smoothing, and did some interpolations so that everything works correctly. Okay, so the biggest challenge was getting the UIDF to match the real hardware, because every tiny modeling error can break motion planning. I solved this by testing the robot joint by joint in Avis, verifying access limits and transforms until everything behaved correctly. I then added safe poses, waypoints, and workspace limits so that the robot moves through the controlled and predictable paths. So MoveIt also required a very careful setup, because motion planning just kept failing and I couldn't see movement in gazebo. So I fixed this by checking the inertial and collision parameters and separated planners and controllers using ROS2 control. And I also followed a strict rule that if something doesn't work in Avis, it doesn't work on the real hardware. And finally, the sim to real gap was another major challenge. What seemed to be working in the simulation just didn't work in the real world, and I fixed this by reducing the acceleration and velocity, added firmware interpolation, and moved to a structured debugging method so that everything works correctly and I can pinpoint the issue. So that's it. Thank you for listening to me. And next, I want to do advanced manipulation, and I want to do also multi-robot coordination and machine learning. And my next project is mobile app control. And I'm also working on Lee robot from Hugging Face, which is a leader follower setup. For that, I'll require bus servos, And by the way, are there any sponsors for this? So thank you, and if you have any projects where I can contribute, please let me know, and I'd be really happy to learn more and keep exploring robotics and ROS and everything that comes up next. Thank you.